let's now start doing what's called as Rankine-Hugoniot relations. So you're not talking about the relation that Rankine has with Hugoniot, but right, but you must have come across Hugoniot when you were doing gas dynamics, for example. So you'd have come across Hugoniot. So what did we do at that time when if you did a gas dynamics course? What you typically do is you are looking for what's called as jump condition across shocks, right? So you want to now treat a shock as a discontinuity and then want to conserve equations across, just saying so much mass came in on this side and it should be equal to so much mass that side, and momentum here equals momentum there, and so on. We try to do something similar here, except that we want to now consider a reaction zone instead of a shock necessarily. The reason why we want to do that obviously is we find that combustion is too complicated, right? So is it possible for us to actually live without combustion, right, or without having to worry about combustion, without having to solve combustion problems? Is it possible for us to actually deduce some gross features for the flow of reactant gases into a reaction zone by looking at what comes out of it in relation to what went in, right, without having to actually look at what happens inside? So we want to now treat the region where the reactions are happening like a black box, and then simply want to look at what's going in and what's coming out, right, and see if we can learn something about that. So the justification for this is that most reactions happen in a very thin zone, and so it's possible for us to actually, we don't necessarily want to say that we are adopting this as like a surface of discontinuity. We don't want to really have like a jump condition across a surface, but it's jump condition across a region. So it could be a little thick, all right, but that's okay. But you know, if it is going to fill up the room, then you're not going to be able to do this. So obviously you want to have it confined to some region across which you can apply jump conditions. So we notice that most reactions take place in a region. So we can treat these regions as discontinuities between conditions corresponding to what we would call as reactants on one side and products on the other side, right? So as a simple case, of course, let's consider a 1D steady situation, right? So consider a steady 1D flow, right, and take a flame fixed coordinate system. That means we are now going to say, if you now had a flame that is occurring over here, we are simply going to say that whatever is coming in at a velocity u0, and what's going out is going at a velocity u infinity, and this has conditions rho naught, p naught, t naught, yi naught, and this has conditions rho infinity, p infinity, t infinity, yi infinity, right. I goes from 1 to n for n species, right. So what that means is, so how did you draw this boundary, right? How do you now decide that what is outside of this region? Outside of this region, outside of this reaction zone, outside the reaction zone, on either side, no gradients are present, no gradients in any quantity, right, is present. That means all the variations are happening only here. That means you started out with a uniform rho naught, p naught, t naught and yi naught. All the jumps that are happening, right, are happening only within this, and then you're now ending up with a t infinity, p infinity, rho infinity and yi infinities on the outside, which is now uniform on the other side. So all the variations are happening there. What that means is, this is now essentially a stationary combustion wave involving not only reactions but also all the heat transfer, viscous effects, diffusion, everything, right, because all the diffusion, heat transfer, viscous effects, all of them depend on gradients, right, and then all the gradients are contained in this. So diffusion, viscous and heat transfer. So maybe I should just write here, that's okay. So that's what's going on within this very small region. Is it okay? Can we do this? Do we have a feel for what's going on? If we were to deal with gas dynamic shocks and treat that as a discontinuity, we will find that the shocks are only about a few mean free paths thick, okay, and that's very thin, strictly speaking. About few is less than 10 mean free paths thick. Over here it's not going to be so bad or so thin, right. So if you now think about like a flame, like in a Bunsen burner, you're expecting it to be less than a millimeter thick or around that, okay. Some conditions it could be around about a millimeter or so. That's still quite small, quite thin, right. That's for a flame. Is it possible for us to now think about like a flame that happens along with a shock wave, right, like reactions happening along with the shock wave? Or in other words, whatever shocks that you have come across were because they were actually propagating in non-reacting inert mixtures. What happens if you now were thinking about shocks propagating in reacting mixtures? What will happen? Will you have reactions that happen along with it, right? So is it possible for us to deduce those? When will we have what kind of a flame? Okay, but in general what you're basically thinking is whatever we are thinking about, it's reasonably thin, it's okay. We can think about this is a little black box that's quite thin, and on either side, and all the gradients are in there, and on either side you have uniform flow of reactants on one side and products on the other side. Okay. Now if I have this picture, this is obviously a flame fixed coordinate system. If I want to have like a lab fixed coordinate system, what do you think will happen? So we now have this u naught coming in here and trying to make this stop, right. That's because we are traveling with the shock. So if you had a still set of reactants and the shock actually tries to go, I shouldn't say shock, strictly speaking, could be a flame, just a reaction zone, right. So this travels like this. That means the reaction zone is eating into the fresh reactants, maybe fresh chilled reactants, right. So this is strictly speaking supposed to go like this. But I now find out, mark my words now, okay, I now find out at what speed this goes, and then try to oppose that with an equal amount of velocity for the reactants to stabilize this, to stay there, okay, and then it will stay. Otherwise I'll have to travel with it. That means I should know at what velocity this goes, so that I can travel along with that to make it stationary with respect to me. So there is a little problem in terms of like having to know what this velocity is. Or shall we get it with this set of equations? That's not true. What we are really hoping for is, if I were to give these, I can get these. But in this problem I don't even know this, strictly speaking. Keep that in mind, okay. That's going to come back and haunt us a little later. So our goal is to obtain product conditions given reactant conditions, right. So question is, are all of that known, okay, specifically U0. I have this question with me, and I have to seek an answer as we go along, but let us suppose at the moment I know what this U0 is and see what happens. Okay. So how are you going to obtain these product conditions? Obviously you have these conservation equations that you want to integrate across the shock or the reaction zone. So mass continuity or mass conservation can be integrated, right, across this discontinuity to give, you can integrate this and then find out that all it matters is you have to substitute the n conditions starting from one side to another side. If you now travel x this way, for example, then you get rho naught u0 equals rho infinity u infinity. You are so familiar with this that you don't even question how we did the integration and got this, right. So I'm just going to take liberties and say this is how we got it, okay. But then if so this is actually the incoming mass flux, and we are now saying that's outgoing mass flux and they are equal. So if they are equal, then can I now say both of them are equal to some common m dot, that is like a mass flux in the system. So the mass flux kind of tells you the size of the or the strength of the system, okay. Higher the mass flux, stronger is your propagation, faster is your propagation. So let's call this equation 1 today. So momentum conservation, so we have rho naught u0 squared plus well, actually strictly speaking we should be able to integrate and say rho u squared plus p minus 4 by 3 mu du by dx equal to a constant. But then we also notice that we want to integrate this, so across this region you don't have this term because you don't have any derivatives when you're now trying to apply this to a left hand side or right hand side. So this can be written as rho naught u0 squared plus p naught equals rho infinity u infinity squared plus p infinity, right. So let's call this 2. This is also something that you're familiar with, but I should take a little bit credit to say that we didn't get this. This is true not just for inviscid flows. This is true even for viscous flows. Okay, so we could actually keep this and try to evaluate it outside the discontinuity and find that du by dx is equal to 0. So it's like you can have viscosity all right, but so long as you don't have velocity gradients, you don't have a viscous effect, right. So the viscous effects are negligible on either side of the discontinuity, and therefore you get it to behave like an inviscid flow. That's how inviscid assumptions typically work, right. Now we want to know, how do we want to do this? Keep in mind, what we want to do is, our goal is to obtain product conditions given reactant conditions, alright. And the way we want to do this is, we want to deal with it in some sort of a thermodynamic fashion. That is, if I were to give you 2 thermodynamic properties that are representing the state of the system when they were reactants, is it possible for me to actually find out corresponding thermodynamic properties for the state of the system when they have become products, right. So it's sort of like a global approach, and we are putting a black box around. We are only worried about what happens between when we started out and when we ended. We are not really worried about how this change happened, right. That's very symbolic or symptomatic of thermodynamics. Therefore I should be interested in describing the initial state of the system thermodynamically, and correspondingly look for obtaining the corresponding thermodynamic quantities that describe the final state, that is the products. Well, I started with mass conservation. I had rho naught and u naught. Rho is certainly a thermodynamic quantity, but u isn't. That's a flow quantity, right. And similarly I can say rho naught u naught squared plus p naught. Rho and p are, but u naught isn't. That's a flow quantity. So is it possible for me to somehow camouflage the flow and then try to deal with only the thermodynamic quantities? The answer is, so long as I'm going to use m dot, okay, and treat it as a given, and keep in mind this is related to u naught, right, and then we can't quite treat it as a given, okay, we don't know exactly, so there's a little problem. But so long as I'm going to couch my u naught or u infinity, either of them as a matter of fact, into m dot, and it's so nicely, it is so nice that both of them can actually get hidden into m dot, okay, this equation will permit us to do that. So I'm going to use m dot whenever I try to get a velocity, right, and then I'm going to write like u naught as m dot divided by rho naught, u infinity as m dot divided by rho infinity. So I try to do that, then so 1 implies rho naught rho infinity u infinity squared minus rho naught u naught squared, as we can write this as m dot squared times 1 over rho infinity minus 1 over rho naught, and that would be equal to, so what am I doing? I took this rho naught u naught squared to the right hand side, so I had this difference, so I have to take this p infinity to the left hand side, and I have a p naught minus p infinity, right. So from this I can write p infinity minus p naught divided by 1 over rho infinity minus 1 over rho naught equal to minus m dot squared, okay. It's very interesting. This analysis is amazing in my opinion. Okay, what you're looking for is to go back and look at the goal again. We are looking for product conditions given the reactant conditions and we just decided that by conditions we will actually talk about thermodynamic quantities, right, and then we just went through these and then found that rho and p are the thermodynamic quantities. So if I were to be able to give rho naught and p naught, I should be able to get p infinity and rho infinity. This is what I am trying to look for, alright, and in trying to get this equation I have already used up the two equations, okay, the mass conservation and momentum conservation. What am I getting out of this? So if I were to plot, and this is the beginning of some lot of fun that we are going to have in the coming days, right, if I'm now going to plot p infinity on the y-axis and 1 over rho infinity on the x-axis. Now keep in mind 1 over rho means specific volume, so this is like a PV plane, right, and if I were to now locate numerically the value of 1 over rho naught and let us say p naught, alright, that is to say I am starting with a modest pressure for the reactants, yeah, and a modest value of 1 over rho naught, that means like a fairly high density, okay, that is what I am starting out with, and this is my initial condition. I am trying to locate for this initial condition where the final condition should be, and this equation is basically telling me that I can look for my final condition anywhere along a straight line, okay, which connects this point to the final condition with a slope equal to what, minus m dot squared, right. Now m dot is mass flux, that can't be negative strictly speaking, okay, it can be negative only if I had the flow going backwards like this. So I am not really thinking about the reactants flowing out of the reaction zone, I am looking at the reactants always feeding into the reaction zone. So I am thinking m dot is positive, that is okay, but m dot squared should obviously be positive, so let us not even worry about it, right, and therefore negative m dot squared is going to be negative. So the slope of this line is going to be negative, so I am going to be looking for a line that always is having a negative slope, you know, that never happens. You want to draw a line that passes through a point and always goes a little bit off away from that point, okay. So we now push the point to wherever the line goes and then say this is the line along which I am expecting the final solution to lie, right, any point along this line is where the final solution should lie. We have made remarkable progress in the last few minutes. What did we do? We now said given the initial conditions described thermodynamically by two quantities, right, we have now zoomed in on the possible solutions to lie along only one line as opposed to a huge plane, right. Until now we could have actually expected the solution to lie anywhere in this plane, but now it is all confined to just one line. That is amazing, right. We have reduced a plane to a possible set of points in a plane to a possible set of points in a line. That is nice, but then there are infinite number of points in a line just as well as there are infinite number of points in a plane. So what is the big deal? It is all infinite number of possibilities, right. So how do I now pick exactly that solution that's going to be lying on this line? I need at least some more information. I should now be looking for this line to intersect with some other line maybe, or there must be some way by which I can choose a particular point along this line, right. So we have exhausted mass conservation and momentum conservation together to now get a line. We now are looking for a energy conservation to help us with trying to locate a point along this line, right. So this is like a very step by step thing, from a plane to a line, from a line to a point is what you're going. So this line is what's called as the Rayleigh line. and the slope of the Rayleigh line is essentially m dot squared. I am not saying negative end of m dot squared because I have already taken the negative sign into account and drawing a line that is inclined from left top to right bottom. Okay, so the slope of the line contains. So what does m dot signify for us? It's actually the flow. The flow information is hidden in m dot, and the slope of the line indicates how fast it is, right? If the line were very shallow, that means its m dot is quite low. If the line were steep, m dot is high. All right, so that's going to tell us how fast the flow is or how slow the flow is. In turn, it's going to tell us how fast the wave would propagate into still reactants or slow. Okay, but that is something that we don't know. Okay, so keep that in mind. So now you look at the energy equation. To get industrial, the energy equation, reduces to h naught plus half u naught squared equals h infinity plus half u infinity squared. Let's call this 3. Now of course you now have to start thinking about what these h naughts and h infinities are. So note that P naught equals rho naught R naught T naught, P infinity equals rho infinity R infinity T infinity. These are specific gas constants, and these are going to be specific to the reactant mixture for R naught and the product mixture for R infinity, right? So which means we should know what's the molecular weight of the mean molecular weight of the reactants and mean molecular weights of the products, which means we need to know the composition of the reactants and composition of the products, which means we know yi naughts, but we have to actually get yi infinity, right? So how do you do that? We have to integrate the species conservation equation. You try to do that. So trying to relate. So well let's just not do that immediately. So before we do that, let's just say know again also h naught is equal to sigma I equals 1 to n yi naught hi naught, where hi naught equals delta hfi superscript naught plus Cp I T naught, assuming calorically perfect gas. If not, you have to write integral T superscript naught to T Cpi dt. Okay, T superscript naught to T subscript naught. Okay, Cpi dt is what you should write, and then similarly h infinity is sigma I equals 1 to n yi infinity hi infinity equals delta hfi superscript naught plus Cpi T infinity. Okay, so in both the cases we are assuming calorically perfect gas here to simplify things for ourselves. Here you can see that the fate of h infinity not only lies with knowing T infinity given T naught, but also in knowing yi infinities given yi naughts. Okay, and the reason why I was talking about yi infinities in relation to yi naughts was to get the mean molecular weights for the reactants and the products, and that's because we wanted to relate the T naughts to P naughts and rho naughts. That's what we are comfortable with. Okay, we are comfortable with P naughts and rho naughts, or P infinity and rho infinity. We wanted to write T naught and T infinity in terms of the pressures and densities rather than keep them as temperatures, for which we wanted to use R infinity and R naught, and that involves molecular weights and involves yi's and so on. That's what we were talking about, but we also find that hi's require yi's for forming your H naughts and H infinity. So we will try to relate yi infinity to yi naught, right? How do you do this? So let's now try to integrate the species conservation equation across the discontinuity, right? So if you now try to equate the species conservation, then the species conservation equation leads to notice what we had. We had for the species conservation the convection term and the diffusion term and the reaction term. Okay, the convection and the diffusion terms involve derivatives, so they don't really exist here, and what really it boils down to is to say that simply your W I naught equal to 0 and W I infinity equal to 0, right? Now you could recall that you can say W I is sigma k small k equals 1 to m W I k, therefore yeah, the W I k, and W I k equals capital W I nu I k double prime minus nu I k single prime omega k. So what this means is, so if you now try to take these two together, right, then this simply means what you're saying is omega k not equal to 0 and omega k infinity equal to 0. This is what it's going to. Of course, you can say that for both of these, you can say k equals 1 to m for each reaction, right? This is for a multi-step reaction. Now here we have a little problem, which is this is all right. This is more or less all right, because your reactions at the end of the reaction zone are going to come to completion. That's how you actually figure out that the reaction zone is over, right? And how did they come to completion? Because you have actually consumed the reactants in those reactions. So if you now look at reactant profiles, they would actually go to 0, or at least one of the reactants will go to 0, and if the reactant concentrations were present in these terms, right, through the law of mass action, you know that the reactant one of the reactant concentrations goes to 0. That means if either of the reactants that are happening in a reaction goes to 0 concentration, then the reaction is complete, is what you are basically thinking about. But here, as far as this is concerned, omega k naught, the question is it 0? In other words, are you having reaction rates equal to 0 here? I thought so, because I thought all these, this is the region that contains all the reactions, right? This is a region that's not supposed to contain any reactions. Is that right? We have all the reactant concentrations, yeah, and then we also have a temperature T0 at which they can react. So strictly speaking, there is nothing that's really stopping reactants at, like, let's say a reactant's temperature, let's say room temperature. There's nothing that's stopping them from reacting. It's just that they have to circumvent the activation energy, and it's take a long time. So the reaction rates are very low, but it's not necessarily 0. So this is going to be some very low number, maybe 10 to the minus 14, but it's not 0, right? So while we are now thinking that you don't have any gradients over here, that's because we are not really taking into account the heat conduction that's happening because of chemical reaction. So there is like a mild gradient possibly, but we are disregarding that, saying that there is like a line that we are drawing and saying no gradients on the other side. Similarly we are also drawing a line saying no reactions there, but that is not going to numerically work out. So this is what is termed as, in most combustion problems, this is what is called as the cold boundary difficulty. Or in other words, if you want to supply an upstream boundary condition on the cold reactants in most combustion wave problems, you will find that it is not really strictly true to say that it is not reacting at all. Alright, but then we suppose, and this is primarily because of the way the Arrhenius law works. The Arrhenius law is essentially an exponential dependence on temperature for the reaction rate constant, and that is not really going to 0 identically as you go to room temperatures or the reactant temperatures. It still exists at a finite non-zero infinitesimal maybe value. So we circumvent this in some sort of an ad hoc manner. Okay, we don't do this perfect way of integrating things across the jump and all that stuff for the species conservation. We could do this for the mass conservation, we could do this for the momentum conservation, we could do this for the energy conservation, but the species conservation is not going to actually lead to this. The reason is this, all these are actually rate equations. Okay, so this is actually a mass flow rate, this is a momentum flux rate, and this is a energy rate, and similarly this is a species flow rate is what the species conservation equations is all about. But what we are primarily looking for is only the composition. We are not really worried about the rate of change of composition or the rate of flux of composition and so on. So we could actually fall back to thermodynamics instead of looking at rate equations like species conservation equation in this case. So typically we sort of blink our eyes on this, don't worry about this, and then resort to thermodynamics. And in thermodynamics we have seen how the product concentrations actually can be worked out given the reactant concentrations, but the caveat there is we are assuming equilibrium, right? Whereas in all these rate processes that we are doing, we are not necessarily assuming equilibrium. That means we are allowing for changes to happen, and it manifests in saying the reactants themselves are undergoing change even far upstream of where you thought was the reaction zone, right? So strictly speaking it says no equilibrium. So we wink our eyes on that, we just say don't worry about it, we will assume equilibrium, we can try to get our y infinities from an equilibrium condition, and recall what we did when we did that. We started out with atom conservation on either side, that is like balancing the chemical reactions for additional equations that we needed for extra unknowns on products. We assumed hypothetical partial formation equilibria and so on. So we had ways by which you could enumerate the y infinities assuming equilibria. So that is what we do. So we overcome this by supposing equilibrium condition for the products and obtain yi infinity given y naught under that framework. Okay, already done before. Okay, so let us suppose that let's not make a big fuss about this. We know how to do this. We can proceed on dealing with the energy equation. So we have the energy equation integrated across the jump, and we call this 3. And of course there as well we have u naught squared, and we don't like to see u naught. We want to replace it with m dot, right? So we use 1 in 3, which means h infinity minus h naught equals minus half m dot squared 1 over rho infinity squared minus 1 over rho naught squared, because we can write u naught squared as m dot squared divided by rho naught squared. And then you can also use you now notice that you have 1 over rho infinity squared minus 1 over rho naught squared can be written as 1 over rho infinity plus 1 over rho naught times 1 over rho infinity minus 1 over rho naught. And then you can find out if now you say this taken over there, minus m dot squared times 1 over minus rho infinity minus 1 over rho naught is p infinity minus p naught. So you could try to use that. So h infinity minus h naught is equal to half 1 over rho infinity plus 1 over rho naught times p infinity minus p naught. This is good because this completely gets rid of m dot, right? Previously we had this Rayleigh line that could actually change its slope depending upon the m dot, but now we have a truly thermodynamic relationship, no flow information at all. That's great, because this is actually related to thermodynamics in some sense. Okay, if you started out with certain energy content in your flow in terms of a mixture of heat of formation and sensible enthalpy, right, you will get your reactants, your products to now have so much enthalpy which will have another combination of heat of formation and sensible enthalpy, right? That's essentially what this means. So we can now further say, well, let's now write this as in fact this is before we do that, let's now, in fact this is what is called as the Rankine-Hugoniot relation. Let's just try to do this a little bit more. Next couple of steps is going to be a bit clumsy, but let's just bear with it and see what happens. So if you now write your h infinity as this and h naught as yi yi naught hi naught, and then you have to write this as sigma I equals 1 to n yi infinity delta hfi naught plus sigma I equals 1 to n yi infinity cp infinity t infinity, this should be cpi, minus sigma I equals 1 to n y naught delta hfi superscript naught plus should say negative again, sigma I equals 1 to n y naught Cpi T naught. Now let's call what happens now. So let's now call this as our H infinity naught, and let's call this is H naught naught. Why would you call this H infinity naught and H naught naught? Because they are actually standard heats of formation of species I weighted by the product composition. Here this is weighted by the reactant composition. So this superscript naught in both the cases actually indicates standard heats, standard conditions, and the infinities and infinity and naught basically means you are weighting with respect to product composition and reactant composition respectively. So this is equal to H infinity naught minus H naught naught plus Cp infinity T infinity minus Cp naught T naught. Why would you say Cp infinity? Because T infinity can be pulled out of the summation. So sigma yi infinity Cpi is Cp infinity, right? Here you're going to get, so this is Cp infinity and this is Cp naught. So it is essentially the compositions that are deciding these terms rather than the heats of formation, standard heats of formation or the temperature there. So this is what you started out with the left hand side. The right hand side can be written now. So this is equal to 1/2 P infinity minus P naught times 1 over rho infinity plus 1 over rho naught, right? Okay, now I told you we don't like T's, temperatures. We want to write things in terms of pressures and densities. So we use our equations of state applied to the end conditions, and if you do that, and in one more step we will hit a point that's ready for us to draw a curve that will intersect with the Rayleigh line and try to get us a solution. So gamma infinity R infinity T infinity divided by gamma infinity minus 1. So Cp is being written as gamma R by gamma minus 1 basically, minus gamma naught R naught T naught divided by gamma naught minus 1 minus 1/2 1 over rho infinity plus 1 over rho naught times P infinity minus P naught. Okay. So you try to take this to the right hand side to the left hand side, and this term you now take to the other side with a negative sign. So we now call this equal to minus H infinity naught minus H naught naught, and we want to call this Q, right? So the negative of the differences in the standard heats of formation weighted by the product composition and the standard heats of formation weighted by the reactant composition is essentially what we are saying as the heat released due to chemical reactions in this, right? So this is exactly what we talked about previously as well. So that is the heats of formation, the difference between those is the one that is actually giving rise to the chemical heat release. So we will just write the next step and stop for the day. So if you now write your R infinity T infinity as P infinity divided by rho infinity, because that's what we are looking for. So P infinity divided by rho infinity minus gamma naught divided by gamma naught minus 1 P naught divided by rho naught minus, of course, keep this equal to Q. This is now clean because it is now coming back to within pressure and density. We are not really having any temperatures anymore. Now for just to simplify, if gamma infinity equal to gamma naught, this is not very bad because gammas are typically about 1.3, 1.4, 1.2 whatever. So we get gamma by gamma minus 1 and P infinity minus, sorry, divided by rho infinity minus P naught divided by rho naught minus half 1 over rho infinity plus 1 over rho naught times P infinity minus P naught equal to Q. We will just start from exactly this point when we meet again. This is equation 5, and what I want you to think about is how is this curve going to look like in this plane. That means given your P naught and 1 over rho naught, look at this curve to find out how in this plane of P infinity to 1 over rho infinity this curve is going to look like. Have a good weekend.